Our today's topic is page replacement algorithm. Before we discuss about different types of page replacement algorithm, we first need to know what is page replacement and why it is needed. See, we can see here our virtual memory. Okay. This is our main memory. This is CPU. What happens actually is main memory size is very less compared to virtual memory. Here I have not made much difference in size because it will not be seen. So I have made almost same size to make it visible. But in real life, virtual memory will be very big and main memory will be small compared to virtual memory. Very small compared to main memory. But process needs to be loaded to main memory for execution. We cannot execute the process if the process is present in the virtual memory. We can see here process P0, P1, P2 and many n number of processes are stored in the virtual memory. Suppose we just want to execute process P1 at the present moment. So for that what we need? We need the process P1 to be loaded from virtual memory to main memory. Now, because main memory size is small, I may not be able to take whole P1 process to main memory from the disk. What I can do, immediately which page has to be executed from this process. We can see here there are process 0 in P1 process. We have page 0, 1, 2, 3, 4, 5. So we can imagine process P1 consists of 5 pages. So which page has to be executed now? That page alone can be taken to main memory, can be executed. Again which page is needed? That can be taken to main memory and can be executed. Why it is needed? Because we can imagine, suppose this portion of main memory is already occupied. I have only this much of free space. This portion also is occupied. So I have only this much of portion available in main memory. Now, how to know which page has to be taken from virtual memory to main memory? Let's say process P1 is executing. It is only CPU who will tell which page should be executed. I will tell you more clearly. CPU will tell execute instruction number 3 or 4 from page number 3. So, which instruction CPU wants to execute? That instruction suppose is present in page 3. So, page 3 has to be taken. After that suppose CPU is telling some instruction has to be executed. If that instruction is present in page 1, then page 1 has to be taken from virtual memory to main memory. Next, CPU is telling some instruction which is present in page 2. So, because that instruction has to be executed, we have to take page P2 of process P1 from virtual memory to main memory. Now, so what I said, if I try to explain you here, what I will tell, see page 3 is first referenced by CPU. Page 3 of process P1 is already present in main memory, yes or no. Either it is already brought or it is not brought. That are the two options. Page 3 is already taken to main memory. So I don't need to bring it from virtual memory to main memory. Next, which byte CPU wants to execute or which instruction CPU wants to fetch is present in page 1. Whether page 1 is available in main memory? No, page 1 is not available in main memory. So what has to be done? Page 1 should be taken from here to main memory. So let me take page 1 from here to main memory. Next, which instruction is needed? Present in page 2. Page 2 is present in main memory before? No. So page 2 should be taken from virtual memory to main memory. Next, which page is needed? Next page needed is 4th page. It is present in the main memory? No, it is not present. So it has to be taken from virtual memory to main memory. Let's say next page needed is page number 5. Which is present in memory? No, it is not present in main memory. So what has to be done is page 5 should be taken from virtual memory to main memory, but no memory space is available. So what we have to do is we need to swap a page. Either 3 should be replaced by 5 or 1, 2, 4, any one of them should be replaced by 5 because 5 has to be brought in main memory. 3, 2, 1 and 4 is already executed. So for bringing 5 from from virtual memory to main memory, I need to replace some page. In the sense that page should be again given back to the virtual memory and page number 5 should be brought from virtual memory to main memory. So let's say I am using what I am following is which page has brought in the beginning, that should be going back to virtual memory, and which page has to be brought from virtual to main memory, that should be taken back. So what will happen? Page 3 should be taken back to CPU. So this space will be empty and page 5 should be taking the place of page 3. So it is not page 3 now. Page 3's place will be replaced by page 5. One more important thing is when we need some page and page is not available in main memory, it is available in disk, it has to be brought. So every time we are bringing a page from virtual memory to main memory is called a page fault. Fault means page is needed, not present in the main memory. So it is a fault. Fault for what? Fault for not having the page in main memory. So it is considered as page fault. So I can tell, see 3 was required by CPU in the beginning, but 3 was already present in main memory. So no page fault for 3. But when 1 was required, 1 was not there, it was brought from virtual memory. So 1 page fault happened for 1. Similarly 2 also was not there, 4 also was not there. So for 2 and 4 also page fault will occur. So for 3 no page fault, for 1, 2, 3 page fault will occur. And continuously like that page fault will be keep on happening because remaining reference pages, suppose now next reference page is suppose 0, which is not available. So again 1 page fault will occur. 1 page has to be replaced. And why page replacement will occur? Because the pages has to be brought to main memory, but main memory is not having sufficient space to keep that page. So 1 page should be taken to virtual memory, and which page is taken, that page will give the free space in memory. In that free space, next referenced page by CPU should be brought from virtual memory to main memory. So that is the main concept behind page replacement. One important thing we should tell, that is page fault is always time consuming because it involves hardware, it involves disk access is slow. So page fault is not at all wanted for the system, but still because of size difference of main memory and virtual memory, and pages should be present in the main memory, otherwise we cannot execute. So page fault is obvious if all the pages of process cannot be accommodated to main memory from virtual memory before starting of the execution. So page fault is an obvious thing which is drawback for the system, but still it happens, and because it happens we need to replace the page, and for that we have page replacement algorithm. We have actually 3 page replacement. What are the 3 page replacement algorithm we have? Fifo, LRU and optimal. Fifo is first in first out, LRU is least recently used, optimal is another type of page replacement algorithm. These are nothing but some rules to follow about which page has to be replaced. So in this present video we will discuss about page replacement algorithm Fifo, first in first out. Definition of Fifo page replacement algorithm is, obviously it is first in first out, and in general if I want to give the definition, it is when a page needs to be replaced, page in the front of the queue is selected for removal. So in simple way we can tell which page has entered first to the main memory, that only should be replaced. As we discussed in the previous discussion, there was a page reference, one small page reference we have considered, which was referred by CPU. Here we have taken a page reference of 70120, like that. This request is coming continuously by CPU, and that pages should be required in the main memory. Initially what we can see, frame is empty. Frame means where we are putting the page coming from virtual memory to main memory. Page size and frame size is same, so one page can be brought to one frame of the main memory. See, here we have provided 3 frames, frame 1, frame 2 and frame 3. First frame 1 should be, we should put data to frame 1, then frame 2, then frame 3. And it is not like we will have always 3 frames provided in main memory. For simplicity, we have assumed only 3 frames are available in main memory. So I cannot use beyond 3 frames, but it is not like that in real life. There may be less number of frames or more number of frames available in the main memory. So let us assume first a reference page which has to be brought from virtual memory to main memory is page 7, where I should keep that page 7. After bringing it from virtual memory to main memory, I should keep it in the frame 1. So 7 should go to frame 1. Next, which reference is coming? 0. 0 is present? No, it is not present. So already one frame is occupied by 7. So which page should be brought now? Page 0 should be brought from virtual memory to main memory. So for corresponding to 7, I will have a page fault. So when I will have a page fault, I am not writing anything down. Okay, when we will not have page fault, I will mark those boxes. See here, so there is a page fault. 7 was not there. 7 was brought from virtual memory. Now one frame is occupied by 7. Next reference is 0. 0 was not present. So 0 was brought from virtual memory to main memory. Next request is coming for 1. 7 was already there, 0 was already there, one frame is free, so 1 was brought from virtual memory and kept to 1. Now when 2 comes, page replacement algorithm is needed. Which algorithm we are following? First come, first serve, or first in, first out, Fifo. It is not first come, first serve, it is first in, first out. So first in, first out means which one was in first? 7 was in first. So 2 should replace 7. No more memory space, it is occupied. So 2 should take the place of 7. So 7 has to go from main memory to virtual memory. 2 will come from virtual memory to main memory. So I will write here 2, remaining will remain same. Once easy way out, I will tell you. Always we cannot keep track which one has entered first. So what we should do? Just count the number. See, at this position, count the number. How many 7s are there? 3. How many 0s are there? 2. How many 1s are there? 1. So easily we can understand 7 has entered first. So 2 should take the place of 7. Next, 0 I need. Whether I have 0 already present? Yes, I have 0 present. So there will not be any page fault. It will remain as it is. It will remain 2, 0 and 1. So you can write 201, or if you don't write also, no problem. If we feel we can write 201, or we may not write anything because no page fault is happening. Page requested is already present. Now we need page 3. Page 3 is present? No, not present. So which one should be replaced? It should be replaced with 0 because 0 has entered first. So I will replace 0 first. Remaining I will keep as it is. Now next reference is for 0. So which one is entered to the memory first? 1 is entered to the memory first. So 0 will be replacing 1. See, you can count. 3 1s are there, 2 2s are there, 1 3s are there. So it is very clear that 1 will be replaced by 0. Remaining will be same as 2 and 3. Now request for 4 is coming. So 4 will be replaced by which one? Obviously 2. So 4, 3 and 0. Now after that request for 2 is coming. Which one has entered before? 3 has entered before. So obviously 2 will take the place of 3, 4 will remain same, 0 will remain same. Now 3 is coming. So which one is existing for a long time? 0 is existing for a 3 times, 2 1 time, 4 2 times. So at that moment, what will be the situation in the memory? 3 will replace 0 because 0 is there for has entered long time back. So actually first before 4 and 2. So 3 will be replacing 0. This will be 2 and 4. Now next reference is for 0, which is for long time present, in the sense which has entered first, 4. So we will replace 0. 0 will replace 4, 2 and 3. Next reference is for 3. No page fault, 3 is present. In that case I am not writing. This is one way you can copy the same value. This is another way, you can just leave it. Now next reference is for 2. 2 is already present. So again there will not be any page fault for 3 as well as for 2. Now next reference is for 1. See, 1 is not present. So 1 has to be, something has to be replaced. So which one will be replaced? 2 is there. 2 is entered first. So 2 will be replaced by 1 and 0 and 3 will remain same. Now next reference is for 2. So 2 will replace which one? See here 0 just entered, here 1 also entered, but 3 has entered long time before. So what we'll do? We'll replace 3 by 2. 1 and 0 will remain same. Again same situation where no page fault. Here 1, so no page fault, 1 is already existing, but next reference is for page 7. So page 7 you can see here it is not existing here. So what we should do? We will replace one among these pages. So which one we will replace? See, 2 is only once occurring, 1 2 times, 0 1 2 3 times. Previously it is 0 is there for a long time. It has entered here, whereas 1 has entered here, 2 has entered here. So 0 must be replaced. So in that case what will be the situation? 7 will be here, 1 then 2. Next reference is coming for, next reference is, sorry, we should not write it here. We should write it 7, then 1, then 2. This is one drawback of not writing. So what we can do? We can just copy the same value to avoid the drawback. No page fault, no page fault. No page fault means automatically the same data will persist. No, nothing should be replaced. After 7, reference for 0 is coming. 0 is not present here. So which one will be replaced? See here 7 just entered, 2 entered here, 1 entered here. So who has first entered? 1 has first entered. So 0 will replace the place of 1. 7 will remain same. 2 will remain same. Next reference is for page 1. 2 is entered first. After that 7. After that 0. You can see the occurrence here. 5 times 2, 1 time 1, 7 times 2 times 7. So who will take the place of 2 will be replaced with 1, 0 and 7. So I think it is clear. We have got 1, 2, 3, 4, 5 times no page fault occurred. How many times page fault occurred? Page fault occurred rest of the all times. I have 20 references. I have counted and written. So how many times we have got actually whichever page reference was there that was already present, that count will come from no page fault. Whenever page fault is not happened means which page reference we wanted to be present in the main memory was present. So that situation count is nothing but called hit. So how many hit we got? 1, 2, 3, 4, 5. 5 hit we got. So obviously 20 minus 5. So 15 miss we got. Miss is nothing but page fault. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times it was a miss. Miss is nothing but page fault. Hit is nothing but when the time where page fault has not happened. In many competitive exams, they will ask what is hit ratio. Hit ratio is nothing but number of hit by total number of page reference. So here number of hit is 5. So it will be nothing but 5 by 20. Sometimes they will ask what is miss ratio. So miss ratio is nothing but number of miss by total number of page references. So number of miss is 15. So the value will be fractional value 15 by 20. Hope you all have understood the concept. And in our next video, we will be discussing LRU and optimal. Thank you so much for having patience.